In this video, we're going to explore directing effects in electrophilic aromatic substitution. What does that mean? It means if there's already a group on the aromatic ring, where does the next group go? So our symbol for a group that's already on the ring for this whole discussion is going to be group A. The three mechanisms, the mechanism that creates ortho product, meta product, and para product, are illustrated here. In particular, the slow step that creates the cyclohexadienyl carbocation. If the ortho electrons are used to make a sigma bond, then this is the original cation formed, and here are its two resonance forms and the mechanism to get from one to the other. Of these three resonance forms for the ortho mechanism, the first resonance form would be the best resonance form if A helps carbocations. It would be the absolute worst resonance form and should be avoided if A hurts cations. We'll review what helps and what hurts shortly. In the meta mechanism, if you use the electrons attached to the meta carbon here, you'll get this original cation which resonates to this one, and that resonates to this one. You'll notice the cation never spends any time on this carbon. None of the resonance forms has the cation there. So this would be the preferred mechanism if A was harmful to cations. You could avoid this situation if you put the group meta. Para situation, your original cation is here, using the para electrons. This is the para position here. The three resonance forms are here. The best resonance form, if A helps cations, is this resonance form here. If A hurts cations, then you want to avoid that resonance form. You would not use this mechanism. You would go with the meta mechanism. All right. What things help cations? Well, the absolute best thing that can help a cation is a group with a lone pair of electrons on the atom attached to the aromatic ring, and that's what I've shown in this box right here. We got a lone pair of electrons on A resonating in. That's the best way to stabilize cations. No octet violations here. Full octets. Better than this one. Second scenario is if A is an alkyl group like a methyl, ethyl, isopropyl, tert-butyl, etc. That's in this box over here. A will hyperconjugate with the carbocation, which is a good thing. Not as good as resonance, but better than not having hyperconjugation. So if A is a hyperconjugator, we like the ortho situation and the para situation because they both result in a cation where A can directly help. None of the resonance forms in situation 3 place the cation on the carbon attached to A, so the meta mechanism will be used if A destabilizes the carbocation. What kind of things help carbocations? A little more specifically, the lone pair on the atom attached to benzene is these four categories here. Each of those has a lone pair. The most freely resonating lone pair will be a nitrogen lone pair of an amino group. Oxygens don't resonate as well. Their lone pairs are held more tightly, but they resonate nonetheless. That would be a phenol or an aryl ether. If there's a carbon group here, that would be an ether. If there's an H there, it's a phenol. this situation of an amide, not quite as good as an amine, because if you recall, and I will illustrate below, an amine resonates only towards the benzene if need be. The amide can resonate either towards the benzene or towards the carbonyl. I'll show that down here. Amide, the resonance you want for this mechanism has the electrons going towards the aromatic ring to stabilize the carbocation. If this competing resonance with the carbonyl is happening, then you're not getting as much stabilization of the aryl carbocation. Exact same story for esters. Not quite as bad because, once again, oxygen doesn't resonate as much as nitrogen, so the competition is less. Still, it puts the order amines top dog, most strongly activating towards electrophilic aromatic substitution. Ortho and para products will predominate, so we can take advantage of the stabilization of the carbocation. Same story to lesser degree for ethers, even lesser degree because of competing resonance for amides and esters. Carbon groups can stabilize carbocations via hyperconjugation. Here's where there's no group on the benzene. That's our baseline. We'll consider that the reaction rate of 1. Everything above here, it has a reaction rate higher than 1. Everything below here and the continuing below is category 3. The highest speeds are these. Much slower, all of these. And the reason these go with the meta for the next group is because the group attached to benzene in any of these functional groups listed to the right, any of these functional groups, is a carbonyl, where the carbon bonded to the benzene would destabilize a carbocation. You'd be putting this slightly positive charge next to a carbocation in one of these boxes here. Do not do that. Go meta. You never have that situation. Same story with a sulfonyl group attached to the aromatic ring, either a sulfonic acid or a sulfonamide. Nitrile, same story. Slightly positive groups are really bad for this reaction. What's worse than a slightly positive group attached to the benzene is a fully positive group as found in nitros and ammonium ions, and very positive nature in a trichloromethyl or trifluoromethyl, which are both pretty common groups found in pharmaceutical agents. So what's the story again? If you have a group on benzene, where does the next group go? This table must be burned into your brain before test 3 so that you can use it. And where things are on this table is just as important as what they do on the table. So let's illustrate with several examples. In our first example, we have a diethylamino group, firmly in category right here. Strongly activating means the reaction will go quite quickly. You're going to get ortho and para products both. Let's see what they look like. You'll get substantial amounts of both para and ortho. The only reason that para is major is that this group has a little bit of bulk to it. Any group there will have more bulk than nothing at all. So that favors the formation of the less sterically hindered para, because the electrophile is less hindered approaching this molecule than it is approaching this molecule, where it is approaching close to A. So whenever you predict ortho-para products, para is generally the major, ortho is the minor. Product below, similar scenario. It's going to be a slightly slower reaction. We're starting with this category down here with an R group like ethyl, but it's still an ortho-para story, and our result will look like this. para major, ortho minor. Group on benzene on this third reaction is chlorine. Chlorine also has lone pairs, so it can help stabilize carbocations. But when you have a chlorine cation like you would in this resonance form here, yes, it has a full octet, but a highly electronegative chlorine with a positive charge is not a very stable thing. It actually slows the process down. So we'll have, of these reactions, the slowest one is this third one so far, and we'll get these results. Here we see in the para product, which is major, the acetyl group is here, and the ortho product, which is minor, the acetyl group is here in the ortho position. And in our final one, we have a meta director on the benzene. We're in this category down here with the nitro on there. The only product you will observe is the meta product shown here. We put a sulfonic acid on in the meta position. We do not see any ortho para products. If we were going to make an ortho para product, we would suffer from destabilization of the intermediates. So to avoid that destabilization, we put the group meta. I know we're getting a little long here, but I think we're going to close out with 3 more examples. And in all of these, we'll already have 2 groups on benzene, and you'll see which group takes priority and why. In this one, we have a group from the top of our list, right here, and a group from lower on the list, our group, right here. This group takes priority. This ortho para director takes priority. The para position's already taken. You cannot take it again. So we want to go ortho to the one that's stronger on the list in terms of activation, so we can take advantage of its ability to stabilize the carbocation. I'm going to put the group here, ortho here. This will be the major product. It's the one that takes advantage of N's ability to resonate with the cation, but only if you put the group ortho or para to the N. Para is taken, so that's not an option. Ortho is your next bet, and that's where you put it, ortho to the diethyl amino, sorry. Next up, same scenario. The ether is higher on the list than the ethyl group. Ether higher than the ethyl group. So that is going to dictate where the next group goes. We want to go para to the ether for major, ortho to the ether for minor, giving these 2 results. Here's the one that's para to the ether. Here's the one that's... Oh, I did not draw the one ortho to the ether. I will have to change that.